In this video, we're going to start subsection 5.2.2, double integrals over type 1 and type 2 regions. So double integrals are defined over rectangles, and so there's some question about how to extend that definition to non-rectangular general regions, and when that extension would even be valid. We're going to sweep all of that under the rug here, and we're going to state the following theorem as if it were a definition and use it that way. So theorem 5.2.1, let f of xy be continuous over closed bounded region D. If D is all the points xy in R2 such that A is less than or equal to B, and g1 of x is less than or equal to y is less than or equal to g2 of x, so that is a type 1 region, then the double integral of f over d dA is an iterated integral that looks like this. The integral from a to b of the integral from g1 of x to g2 of x of f of x y, and g2, these are y bounds, so that is dy, and then ab are x bounds, dx. So we have variables in the bounds. Now, if we have d as h every point x, y in, again, R2, such that h1 of y is less than or equal to x is less than or equal to h2 of y, and c is less than or equal to y is less than or equal to d, so that is a type 2 region, then the double integral of f of xy over d dA is also an iterated integral, but in the opposite order. So it's the integral from c to d of the integral from h1 of y to h2 of y of f of xy dx dy. So let's go and use these in the next example to see what variable bounds look like, and then in the next video we'll see how to actually go about evaluating iterated integrals with variable bounds. So example 5.2.3, we're asked to express the double integral over d of f of x y dA as an iterated integral of each type, type 1 and type 2, where d is the closed disk of radius 3 centered at the origin. So let's draw ourselves a disk D. So that is, if it's of radius 3, this is from minus 3 to 3, that's the equation x squared plus y squared is equal to 3 squared, or 9. We need to write this D1 as bounds in x, so clearly we've got minus 3 is less than or equal to x is less than or equal to 3 as the left-right bounds in x. Now we have to write this as top-bottom bounds in y. So we're going to split up this circle and solve for y. The top is going to be y is the square root of 9 minus x squared, and the bottom bound, which I'll write in blue, here is y is minus the square root of 9 minus x squared. And so our region D will be, well, the negative root of 9 minus x squared is less than or equal to y is less than or equal to the root of 9 minus x squared. And we can use this, therefore, to write the double integral. So the double integral over this region D, right, this is our region D, of any f of xy dA, where it is continuous on this region, is the double integral iterated from minus 3 to 3, and then from, and this is going to be a little tight to write, the root of 9 minus x squared as the bottom bound up to the root of 9 minus x squared positive as the top bound of f of xy d, and we've got to get the order right. These are functions y is equal to, so dy dx. There it is of type 1. Now let's go and rewrite the whole thing as a type 2 iterated integral. So we're going to want to take our disk again. Let's do it in ink that'll stick. And now we have to write this in terms of constants in y. So again, minus 3 to 3. and we need a left bound and a right bound. So the right bound, if we take the circle now and solve for x, our right bound is going to be x is equal to the positive root of 9 minus y squared. And the left bound is going to be x is equal to negative the root of 9 minus y squared. And so that region D, I called it D1 for the first time. I'm not sure why. That should just have been D. That region, which is still D, is described in a type 2 fashion. So minus 3 is less than or equal to x is less than or equal to, minus 3 is less than or equal to y is less than or equal to 3. And then the negative root of 9 minus y squared is less than or equal to x is less than or equal to, I pinned myself in here a little bit, 9 minus y squared. There it is as a type 2 region. And so the double integral over d of f of xy dA as a type 2 region can be written as the double integral from minus 3 to 3 from the root, the negative root of 9 minus y squared up to the root of 9 minus y squared of f of x, y, and this time we are doing dx, dy. So in the next video, we are going to not only set up the integral, but we'll have an actual function, and we will evaluate the iterated integrals over a non-rectangular region D.